One of the foundational principles of special relativity is that light always travels at the same constant speed. The speed of light is fast, but it still takes 8.3 minutes to travel the enormous distance from the sun to the Earth. This means that if the sun were to suddenly change brightness, there would be a delay of 8.3 minutes before we would see the change here on Earth. Suppose that powerful aliens with advanced technology managed to change the sun's gravity, maybe by removing a big blob of hot gas. Removing the gas also causes the sun to dim at the same time. If we calculate the gravitational attraction between the sun and the Earth, Newton's equations have no time dependence. If the sun's mass suddenly changes, as it would if aliens removed a large portion of gas, Newton would have predicted that the Earth would feel a different force due to gravity instantaneously, with no delay. If gravity changes instantaneously, as Newton predicted, it would still take the photons emitted by the sun 8.3 minutes to reach the Earth, revealing the aliens' actions as the sun becomes dimmer. This means that we could receive information about changes to the sun at a speed faster than light by using gravity. This instantaneous transmission of information is sometimes called action at a distance. Einstein realized that Newton's theory of gravity was wrong because it implies that action at a distance takes place, and that gravity could transmit information faster than the speed of light. Although there were no experiments Einstein could conduct that showed that action at a distance is incorrect, Einstein knew that it would imply that there could be ways to transmit information at speeds faster than light, which would contradict the principles of special relativity. Einstein theorized that gravity could be made compatible with special relativity if changes in gravitational fields are transmitted by gravitational waves that obey the speed of light limit in the universe. Gravitational waves, also called gravitational radiation, are an important part of Einstein's general theory of relativity. Let's return to the aliens who are changing the sun's mass and brightness. Einstein's theory predicts that it takes 8.3 minutes for the gravitational force felt by the Earth to change. So changes in gravity travel at the same speed as light. The relationship between the force of gravity and gravitational radiation is similar to the relation between electrostatic forces and the emission of electromagnetic radiation or light. An electron or a proton are just two examples of charged particles, which create an electrostatic field. Electrostatic fields can be attractive if the force is between opposite charges, or repulsive if the force is between same charges. By rubbing a balloon against your head, you cause negative charges, or electrons, from your hair to migrate to the balloon, leaving your head positively charged. If you then hold the negatively charged balloon near your positively charged head, your hairs will stand up, following electrostatic field lines. The word static means that the system doesn't change with time. A positive charge, like some hair, will feel an attractive electrostatic force that will feel a force towards the negatively charged balloon. The electric field of the balloon influences nearby objects, but in a static system, there is no electromagnetic radiation or light emitted in this situation. If we want to produce electromagnetic radiation, we need to create periodic changes in the static charges. This can be accomplished by changing the position of a charged balloon, say by waving it back and forth rapidly. Positively charged hair will be attracted first in one direction, then the other, and so on. This is a situation which produces a time-changing electric and magnetic field that causes a disturbance called electromagnetic radiation, also known as light. For example, if the balloon is moved back and forth once per second, It generates a changing electric field that moves away from the source at the speed of light. One complete cycle of the balloon corresponds to one cycle of the light wave. So if the balloon moves at 1 hertz, it produces a photon with a wavelength equal to the distance light travels in 1 second. That's 299,792 kilometers, a photon at the very long end of the wavelength spectrum in the radio frequencies. This electromagnetic wave travels at the speed of light, perpendicular to the motion that the balloon is being waved. Information about the changing balloon's position reaches your hair after a time equal to the distance divided by the speed of light. When the wave passes by a charged particle, the particle will feel a time-changing force that will cause it to oscillate back and forth in a direction perpendicular to the direction the wave travels in. Normally, we don't use balloons to create electromagnetic waves. Instead, we might have an alternating current traveling through a dipole antenna to create radio waves, a long wavelength form of light. The important thing to know is that light is only emitted when there are time-changing electric charges or magnets. A star or planet has a gravitational field that doesn't change with time. And unlike electrostatic forces, gravity is only attractive. A small mass placed near a heavy planet will feel an attractive gravitational force that will pull it towards the surface. If there is no motion of the masses, there will be no gravitational radiation emitted. Just like the electrostatic example, in order to excite gravitational waves, we're going to need a gravitational field that changes with time. When gravitational waves are created, they move away from their source at the speed of light. And as the wave moves, it distorts space-time by stretching and compressing spatial dimensions periodically in the 2 directions perpendicular to the direction that the wave travels. These waves are called transverse waves and can be understood in a simplified sense by the analogy of a transverse wave on this rope that Curtis and Ross are playing with. In this video, we see Ross waving the rope up and down, which is sort of like a gravitational wave source. The wave travels along the rope horizontally from left to right and then from right to left. At each point between Ross and Curtis, the rope is forced to move up and down at the same frequency as Ross's hand. In a transverse wave, the movement of the medium is in a different direction than the direction that the wave travels in. A gravitational wave is a wave in space-time, which means that instead of moving objects, a gravity wave compresses and decompresses space-time. Suppose that a gravitational wave travels from the ceiling to the floor through my body. Focus on my arms. The effect of the gravitational wave will be to stretch one arm outwards and compress the other arm inwards. Then the second part of the wave's periodic motion will cause the opposite changes in each arm. Periodic motions of my arm will then occur when the wave travels through my body. If a gravitational wave were to pass by your ear, it would cause your eardrum to start vibrating, so that you could, in principle, hear a gravitational wave if you had sensitive enough ears. For this reason, scientists often convert gravitational waves into equivalent sound waves, which is how we got the chirp sound of 2 merging black holes. In reality, the waves are very weak, and the change in arm lengths are microscopic. In the Star Trek Next Generation episode called Hero Worship, the Enterprise is violently rocked by gravitational waves. This is rather difficult to understand, since in reality, the waves are very weak, and the Enterprise would have had to have been right next to a ridiculously strong explosive event in order to get such a strong rocking event. Scientists on Earth have been working hard for decades to build detectors sensitive enough to detect gravitational waves and directly detected them for the first time in 2015.